Hello everyone. In this video we'll be talking about entropy, which is essentially how we measure the disorder of a system, and it's symbolized by the letter S in thermodynamics. So entropy is one of our state functions, and it's how we're going to look at a chemical system and its organization. Is it more ordered or is it more disordered? So enthalpy, which we looked at before, sounds similar to entropy, so try not to get those two confused. Entropy is one of my favorite concepts in chemistry because it's so, I think, a little abstract. Entropy is a little different than Gibbs free energy and enthalpy. It's a little more esoteric, which I really like. Because you're dealing more with a concept, disorder. But entropy allows us to slap some numbers on what exactly disorder looks like in a system. Entropy is also pretty interesting because we can look at a reaction and pretty well predict what the entropy is going to look like for that reaction. You can't always necessarily do that with delta G or with delta H, with Gibbs free energy or enthalpy. But entropy, you can look at a reaction and a lot of the time you can actually make a pretty solid prediction on what the entropy is going to look like for that reaction, whether it's greater than 0 or whether it's less than 0. So when we think about a chemical system and entropy, particularly when we look at an increase in overall entropy, what we're looking at is a system that goes from an area of more organization and it moves into an area or a system of less organization. We become more disordered as we increase our entropy. And so this is pretty analogous to how most students are at the beginning of a semester versus the end of the semester. At the beginning of the semester, we're usually pretty organized. We have all our papers organized, we have pencils and books, we tend to be pretty neat and tidy. Think about in high school, your locker usually looks pretty good at the beginning of the semester. You got all your stuff where you want it. By the end of the semester, we're usually pretty highly disorganized. Papers are everywhere. Books are everywhere. We don't know where our pencils are at. We don't know where anything's at. So pretty similar to chemical systems. In a system where we have that disorganization, we consider that to be high in entropy. So we're just going to look at briefly at some examples where we typically see increases of entropy, and this is what you can look for when you go trying to predict what the entropy is going to be for the reaction that you're looking at. So we're typically going to see an increase of entropy with the following situations. So going from a solid to a liquid when you melt a substance. So when you melt something, you're going from a solid, which is a tightly knit system, a very organized system. Think about a block of ice. It's crystalline. Those molecules of water are packed together very tightly, very organized, very low amount of entropy. You melt it, it becomes a liquid, it becomes more disorganized. It's fluid, it's more dynamic, it's flowing. You've got a flow of molecules going on. So you're increasing the entropy, you're increasing the disorder, going from that solid crystalline structure to a flowing effluvious structure or system. And that would be an example of an area or system where we're increasing the entropy, we're increasing the disorder. Same can be said for evaporation. So when we go from a liquid to a gas, same thing happens. You go from a liquid, which is a loosely organized system, to a gas, which is a very disorganized system. So we increase our entropy there. Gases have the highest level of entropy of any of the states of matter. So gases are sort of the pinnacle of entropy. And of course, when you kind of jump the gun and you sublimate, when you go from a solid to a gas, you're going to increase your disorder, because of course you're going from a solid, which again is that very organized crystalline structure, to a gas, which is a very loose, disorganized structure. So think about a block of dry ice. Dry ice, of course, is just frozen carbon dioxide. You take out a block of CO2, dry ice, and all of a sudden it starts fogging. It creates that very dense, sort of cloudy fog when you pull it out into the air. And when it sublimates, it's increasing in disorder. Also, when we have a reaction that generates more moles of gas than you started with. So when you generate more molecules of gas, you're increasing disorder because you're making more gas. Like I said, gas is the pinnacle of entropy. The more gas you create, you're increasing the entropy of a system. And of course, dissociation into ions. So you can look at this like dissolving a solid, or like splitting apart an acid or a base. So think, for example, hydrochloric acid, HCl. When you dissociate the HCl into H plus and Cl minus, you're increasing the entropy of the system. So those are some general things to look for. Now, if we want to translate this prediction into something that looks a little more numerical, let's say we have the following system. Let's say we have liquid ammonia going to gaseous ammonia. It's evaporating and forming vapor. We can predict that this is going to have an increased entropy. So what we can say is that delta S is going to be greater than 0, because we're having that increased entropy going from a liquid to a gas, more disorganized, more disordered. But let's say we go from 2 molecules of NO2 gas and we go to 1 molecule of N2O4 gas. So we're going from 2 molecules of gas to 1 molecule of gas. So we can predict that our entropy is going to be decreased. We're decreasing the disorder because we're decreasing the number of gas molecules in our system. We're becoming more organized. Now, if we went in the reverse direction and we took N2O4 and we created 2 NO2 molecules from that, then we would see an increase of disorder because we're creating more gas molecules. But in this case, we're creating less gas molecules, so we're decreasing our entropy. Our entropy is going to be negative, less than 0. So let's look at an actual calculation involving the delta S of a reaction. So let's say we had the following reaction. So we have 2SO3 gas going to O2 plus 2SO2. And then we have some values for delta S beneath. Now I would like to point out a very helpful hint. When you look these up in a table online like I did, these values, keep in mind that entropy is typically tabulated as joules per mole times Kelvin. If you remember, enthalpy and Gibbs free energy are typically calculated and tabulated in terms of kilojoules. So So just keep in mind that your delta S values are going to mostly be, almost all the time, shown in joules. So that will be important when you go to do some Gibbs free energy calculations. Won't necessarily be very important here, but just keep in mind of your units, because nothing is worse than putting your answers the wrong units. So always pay attention to what the question asks you to put your units in. If it calls for kilojoules and you're doing something with delta S, keep in mind you'll have to convert, because your delta S value will be in joules. With that aside, we can now go ahead and set this up. So if you remember how we calculated delta H of a reaction, we're going to use the same approach with delta S. And so your delta S of the reaction is going to equal the sum of the N products minus the sum of the N reactants. And remember, the N is representing the stoichiometric coefficients of each product and each reactant. So keep these coefficients in mind as you go through to do the calculations. So if we set this up, for our reaction, this is what we're looking for. So we're trying to calculate the delta S of this reaction under standard conditions. I would like to iterate, we're doing this under standard conditions. So what we'll have is we'll start with our products. So we'll have the O2 value, which is 205.02 plus 2 times the SO2 value, which is 248.11, and remember this 2 is coming from this 2 up here. So remember to multiply your values by the coefficients that come in front of each of those compounds. And we're going to subtract this from 2 times the value for SO3, which is 256.65. And if you want to go ahead and pause the video really quick and do this in your calculator, feel free. And so for your answer, you should end up with 187.94. And remember your units, joules over mole times Kelvin. And this will be your final answer. And just before we go, I would like to add one little tidbit which I think is a really, really cool concept. So when you have a spontaneous reaction, you increase the entropy of the universe. So all spontaneous reactions generate an increase of the entropy of the universe, which I personally think is really, really cool. Throughout your life, you conduct so many spontaneous reactions through your bodily functions and things that you'll do as you study chemistry or biology. You'll do reactions that are spontaneous, and you'll study spontaneous reactions. And all the spontaneous reactions in your body increase the entropy of the universe. So you're increasing the disorder of the universe just by existing, which I think is really, really cool. So we'll end there, to say the least. That's just a little tidbit. And it's also important to keep in mind that spontaneous reactions result in an increase of the entropy of the universe. Non-spontaneous reactions result in a decrease of the entropy of the universe. So we'll end on that note, and this is how you'll use entropy and changes in entropy to calculate entropies of a reaction, and also how you can use certain prediction qualities in order to predict what the entropy of a reaction probably will look like. There you go.